Hello, people at Armel. Here's what's up. I decided, that I'll do the really cool, interesting, exciting, theoretical, never before been done inside the walls of Blair High School lesson. Yeah, I think so. On this optional topic. So you can either watch this video or not, I don't care. And then we'll do the thing that's actually like part of the curriculum of this class all together on Monday when everyone's here. Okay, good. So what is the goal for today? We're going to prove that E exists. All right, what does that even mean? What is E?
It's the limit of the continuously compounding interest.
Yes, it is the limit of the continuously compounding interest problem, or it's like, yeah, what?
The limit as n approaches infinity of quantity 1 plus 1 over n quantity to the n.
Yeah. Okay, so that's pretty cool. And yes, you're both right. We define E to be this limit, it came up as a solution to what happens if you try to invest $1 at 100% interest for 1 year, and you let the number of compoundings approach infinity. And when we did this, there was some kind of justification for feeling like this should not go to 1 or infinity. Do you remember this conversation? Where we were like, if you take a number which is just a tiny bit more than 1 and raise it to a larger and larger power, this is going to go to infinity. Yeah. Whereas, on the other hand, if you raise a number which is getting closer and closer to 1 to some constant, however large power, that's going to go to 1. Okay, so it's this exponent which is making the thing want to just keep growing and growing and growing up to infinity, but it's this number getting bigger, making the thing that we're raising to the power closer and closer to 1. So on the other hand, it feels like it should be approaching 1. But these two somehow balance each other out. We end up with 2.7 for some mysterious reason. And when I have taught this before a million times, as I do all like Algebra 2 teachers across America, they just expect you to just accept the fact that this does happen, that we get this number 2.7. So, and certainly you can, so what you can do is you can define a sequence and let that sequence be 1 plus 1 over n to the n, and you can just investigate what happens to this sequence. So like, what's A1, for example? 2. That's consistent with the amount of money you have at the end of the year if you're investing 100% interest for 1 year. How much money, how about, what's A2?
9/4.
It's like 9/4. And A3 ends up being like, what is that? 4/3 skewed. So it's like
64/27.
Yeah. Okay. So like, etc. And apparently this goes to approximately 2.71 eventually. Okay, but I don't fully understand why, and even that it approaches that number is not obvious at all. Good. Well, we're going to do it right now. And this is there's a good reason why this is not normally done in like Algebra 2. It's because it's really hard. And it requires that you have a mastery of other topics like sequences, the binomial theorem, proof by induction, and also some like extremely fancy advanced properties of calculus, which conveniently is like not so different from some other calculus stuff we already did, so it's going to be okay. Alright, so yeah, even like in calculus at Blair, no one does this proof, so that's exciting. Okay, what are we going to do? First, I'm going to prove, never mind why, that this sequence is increasing. That seems important. Okay, so claim AN is increasing. Okay. Well, let's do it. Here's what we do. We take this sequence, which is 1 plus 1 over n to the n, and basically I'm going to do, the only thing I really can do with this is apply the binomial theorem. Okay, so I'm going to go like kind of very slow and careful. On the internet they do this whole thing in like 3 steps, but I'm going to do it in like 10 steps. Let's just start cranking out the binomial theorem. The binomial theorem says if you raise a binomial to a certain power, then you're going to have, you're going to have a sum of a bunch of things, and the kth term in the expansion is going to have form. You're supposed to talk.
Oh.
And
Oh, what?
And it's just
Okay. And then it's like times like that number to the n minus k, and then 1 over n.
Other number to the.
Yeah, that's exactly right. Okay, so we can write this out as the sum. So we can just simplify this slightly. So we have n choose k, and then yeah, that's just 1, so duh, and this is just like 1 over n to the k. Okay. Well, now I will do something cool. Oh, and let's not forget that really this is just, so what, you know, like what is n choose k? It's just n factorial over n minus k factorial k factorial. Okay. Are we still in frame? Just. Okay. So now here is what I will do. I will just kind of simplify that binomial coefficient a little bit. So this is really from 0 to n of n factorial. So right, so like the n minus k factorial cancels out most of the factors in the tailing factorial here, except to like up to like a certain point. So really, this is like n minus 1, n minus 2, and I stop at what's the last one?
n minus k plus 1.
Yeah, it's like n minus, and then this would be like k minus 1. Hey, welcome.
Hey.
Did I do that right? Yeah, that's what you guys did, same thing. So all of that, and that's of course still all over k factorial, and yeah, and then we have the 1 over n. Okay. Okay, so now, so far nothing cool. All right, now I finally start like doing something. And I'll just write this out one more time as, so I guess I'm not really doing anything yet. I'll just think of this as a whole bunch of things, each of which is over n. So this is really like n over n times n minus 1 over n. Because I guess it's worth mentioning, how many of these factors do we have up here? I think
K plus no.
I think it's precisely k of them, right? Because it's like n minus
Yeah.
0, then n minus
Yeah.
1, then n minus 2, we go all the way up to n minus k minus 1. So that's k of these. So each of them matches one of the n's down here, I guess is the point. So I have n over n minus 1 over n, n minus 2 over n, you know, etc., all the way until we get to n minus k minus 1 over n, and then we still have the times 1 over k factorial. I think it's probably just out of frame now. Okay. Yeah, good. Or maybe now I'll just kind of do this. Yeah.
You shouldn't be able to like move.
Okay.
This.
No, it's fine. I know. Okay, good. Well, now I claim it's time to actually kind of start doing something. So here's what I'm going to do. I'm going to take this, and I'm going to, so this is the sum from k equals 0 to n of 1 over k factorial. And already do we see that like each of these is less than 1, right? Because the fraction, or just 1.
Yeah.
So the n over n just dies, that's just 1, that's just gone. N minus 1 over n can be rewritten as 1 minus 1 over n. This one is 1 minus 2 over n, all the way to the last one, which is 1 minus k minus 1 over n. Yeah. Okay. So what I've done is to express each. Remember now, this product is only like a single term in this sum, right? Okay. So, and now that I canceled the n over n, how many of these factors remain? How many factors are there?
K minus 1.
Yeah, there are k minus 1 of them, because we start with 1 and we go up to k minus 1. Okay. Claim, and this claim is kind of like a duh. Let's see if I have, am I in frame? I am well in frame. Claim, well, okay, actually, before I make the claim, I'll just write what it is I'm trying to do. I'm trying to show that the function is increasing. So to show that it is increasing, I should consider the next term, right? So this is a sub n. What does a sub n plus 1 look like? What does it look like? Well, it's just the same crap, right? But now everything just goes up a number. So this is going to be the sum from k equals 0 to, actually, is this the best way to do it? Kind of is. Sure. So the sum from k equals 0 to n plus 1 of 1 over k factorial times 1 minus 1 over n plus 1 times 1 minus 2 over n plus 1 all the way to 1 minus k minus 1 over n plus 1. All right, now say something intelligent about the number of terms, number of factors, etc.
So the number of terms is the same, but the factors are all getting smaller. No, bigger.
Wait.
They're all getting bigger.
Careful, because term means, okay, so I think you kind of get it, but someone else.
The same number of things are getting multiplied.
Yes. This is also, I still have k minus 1, I still have k minus 1 factors.
You have one more term.
But there is one more term, right?
Yeah.
Okay, so if you look at, a sub n is, via the binomial expansion, if you raise something to the n, it's going to have, well, it's going to have a lot of terms, but it's going to, specifically it's going to have n plus 1 of them. We can just see right now, right, with this sum. And this is going to have n plus 2 terms in it. But for each particular term, the term represented this way is directly comparable because there are k minus 1 factors. Additionally, do you see a relationship between this and this?
1 over n plus 1 is smaller.
Yeah, this one is smaller, right? And that's just a simple claim, right? N is less than n plus 1, so 1 over n is greater than 1 over n plus 1. And then if you throw a negative in there, the inequality flips again. Everyone with me?
Yeah.
And then you can just throw in a 1. So I just proved the properties of inequalities, the kind of obvious claim that this is going to be less than this because I'm subtracting something bigger, because this fraction is bigger. And then, additionally, so we can just write similarly, this holds for the next comparison, right? So 1 minus 2 over n is also less than 1 minus 2 over n plus 1, and 1 minus 3 over n is less than 1 minus 3 over n plus 1, etc.
Yeah.
So if you put that all together, what you end up with is, maybe I'll kind of try to squeeze it over here or something. The conclusion of this is, well, now if I take all of these inequalities, each of these inequalities, here's one, here's another one, and just multiply them, then it's clear that overall, 1 minus 1 over n times 1 minus 2 over n all the way to 1 minus k minus 1 over n is going to be less than 1 minus 1 over n plus 1 times 1 minus 2 over n plus 1 all the way to 1 minus k minus 1 over n plus 1. Who's with me?
I agree.
Just multiplying all those inequalities. And then I could also just throw a 1 over k factorial in there. That's not going to change anything. And now what I've essentially showed is that the kth term in the sum representing a sub n is guaranteed to be less than the kth term in the sum in the sum which represents a sub n plus 1. Okay, and then so now what I can do is I can just sum them up, right? So if that's true for the kth term, then it must be true for each of the sums, right? And therefore what I get is the sum from k equals 0 to n must be, do I want to do this whole thing? Sure. The sum from k equals 0 to n of 1 over k factorial times 1 minus 1 over n, 1 minus 2 over n, all the way to 1 minus k minus 1 over n has to be less than the sum from k equals 0 to n plus 1, no, just still n, of 1 over k factorial, 1 minus 1 over n plus 1. Okay, but now, I mean, you know, depending on how loose we want to be, are you guys kind of already seeing that we're sort of done?
Yep.
Why? We have to like technically show that there's
because a to the n plus 1 minus a sub n plus 1 minus a sub n is always positive. So
yeah, because that's right. Yeah, I mean, basically, even if I even if I don't even use all the terms of a sub n, it's already bigger. That's the kind of loose. That's one kind of loose way of saying it, right?
Not loosely do that.
If you want to be a little bit more formal, which I've already sort of started, this on the left now just is a sub n, right?
Right.
So therefore, what I can now say is that a sub n is less than this. And what is this? This is a n plus 1 minus the last term.
Right.
Okay, so a sub n is less than a sub n minus a sub n plus 1, and then minus, that's just what the right-hand side of this inequality is. It's a sub n plus 1 minus the last term in the binomial expansion. And what is the n plus first term? If you think about a sub n plus 1 is going to be 1 plus 1 over n plus 1 to the n plus 1. Just using what you know about the binomial theorem. What does the last term look like? The n plus, it's like the k equals n plus 1 term.
Yeah. N plus 1 to the n plus 1.
Yep, it's 1 over n plus 1 to the n plus 1. Which is obviously positive. Like everything's positive here.
Okay.
Thus, if a sub n is less than, you know, this minus something, then it's certainly less than it. All right. That proves pretty damn rigorously that indeed this sequence is increasing. Everyone cool?
But then now I can
Okay.
claim it's unbounded.
So now you might wonder, what is the point of showing? What is the point of showing that the sequence is increasing? Well, the point of showing that the sequence is increasing is because it. So what does this? What do the terms of this sequence look like? Well, we can sort of plot them now, right? So here's when we plug in 1, we got 2. No, yeah. When we plug in 2, we got 9/4. When we plug in 3, we got some other number. So they seem to be getting bigger, and in fact now we can say they definitely are getting bigger. Okay, theorem from calculus. If you can show that all the terms in the sequence are below a certain upper bound, like, I don't know, 3, then it is a theorem, and it's called the, like, I forget what it's called. It's called like the bounded monotonic convergence theorem, I think is what it's called. Bounded monotonic.
just put all the words together.
That sounds like that might be the title. And basically what it says, what the bounded monotonic convergence theorem says is if you have a sequence, and that sequence is monotonic, which means either increasing or decreasing, or non-decreasing, not increasing, and we just proved this is, and it has an upper bound, then it must have a limit. This kind of feels right, because if something's just getting bigger and bigger and bigger, but also never goes above something, then it's got to stop somewhere. And in fact, what I'm going to do on the next board is show that this never goes above 3. And so the limit has to be something less than 3. Okay, so there's more to say on this, and in fact, this is a case of when you take calculus next year, you will just, I think, just be
That's just the end test, right? I mean, it's in series.
sort of. It's the converse of that, or something.
Oh,
No, yeah, something like. No, it's different. I think this is a very low level theorem, which I think most AP Calc classes would just not even mention it at all, or they might mention it and they certainly wouldn't prove it. Our textbook actually does prove it, but they prove it based on an even more low level fact about the real numbers, which is that they are so-called complete. No real numbers are missing. In fact, I'm prepared to possibly say more about this, but it seems like we shouldn't. Maybe if there's more time at the end, we can talk more about there is one of the reasons why this is considered such an advanced topic is it uses, the proof of this theorem uses facts about the real numbers, which only emerged as being important in like the 19th century. And in particular, I think I might have made some sort of vague reference to this in like September when I casually asked you guys, hey, what's the difference between the rational numbers and the real numbers? Because after all, aren't they both ordered fields, dense ordered fields? And the answer is they are. Both the rationals and the reals have all those properties, like there's the additive inverse, there's a multiplicative inverse, they're closed, there's associative property, there's distributive property, etc. They're both dense. So somehow there must be some property that the real numbers have that the rationals don't, and this is that property. It's called the least upper bound property. And this is the kind of thing you definitely do not do in high school. You do it in college, if ever.
Supremum.
Yeah, it has its own, it has a supremum. Yeah, we talk about this in logic math. So using that axiom of the real numbers, we can prove, and I guess you'll do it next year in calculus, this bounded monotonic convergence. All right, do you accept?
I accept. Yes.
Good. All right. So now I'm going to do something which is also not easy. Can you maybe move it, change seats? I am now going to prove that this sequence is less than 3. Okay, let's do it. Why is this sequence less than 3? So, show a sub n equals 1 plus 1 over n to the n is bounded above. Alright, well, the only thing I can do is just do the binomial theorem again, right? So, if we expand this out, this is the sum from k equals 0 to n of n factorial over n minus k factorial k factorial times 1 over n to the k. Okay. And now I'm going to write this out in a more kind of standardish way by splitting it up into a bunch of terms. So what's the 0th term look like? Well, it's just n choose 0 times 1 over n to the 0. And then this is n choose 1 times 1 over n to the 1. And n choose 2. I'm going to go out for a couple. 1 over n squared. N choose 3. 1 over n cubed. And now I'm going to go to the kth term, the general term. What does the kth term look like? It's n choose k 1 over n to the k. And then we go out to the last term, the k equals n term, which is just n choose n times 1 over n to the n. Okay. Cool. Now, what I'm going to do is just expand those binomial coefficients out a little bit more, kind of like how I did before. So, let's see. Well, what is n choose 0?
1.
It's just 1, and n to the 0 is also just 1. So this first term is just 1. Okay, that's cool. N choose 1 is just n, and that's just n, so this is also just a 1. Okay, what's n choose 2? Well, n choose 2 is like n times and it's just like n minus 1 over 2, right? Yeah. Times 1 over n squared. And what n choose 3? Well, that's like n minus 1, n minus 2 over 3 factorial. Maybe I want to write factorial here too, just to be cool. Times 1 over n cubed. And then the general term looks like n minus 1, n minus 2, all the way out to n minus k minus 1 again, right? K minus 1 all over k factorial. And then the last term, I think I'm going to run out of space, is n, do I want to do that? Yeah. n minus 1, n minus 2, all the way down to basically to 1, which is just really n minus 1 over, did I forget something? I did. I forgot the 1 over n to the k. 1 over n to the k. And then this is n factorial, and then times 1 over n to the n. Okay. Am I still in frame? Oh yeah, well in frame. Well in frame. Okay. What the hell now? Well, claim, maybe you guys see something. If you look at this, if you kind of look at this piece.
Yeah, you can like cancel some stuff.
Well,
Kind of. Right?
Well, n to the k
Well, it's
is
all
always
gonna be less
greater
than
than the thing on the top.
yeah, William's like, yo, n squared has to be bigger than n times n minus 1, of course, right? And then n cubed has to be bigger than those. And then that's just like always going to be true. Okay, so claim, can someone rotate the camera over here? Claim, so now just do like a little lemma. Let's just do like lemma. Claim that, my claim is that n times n minus 1 times n minus 2 all the way to n minus k minus 1, in other words the general term, over n to the k is less than 1. And I mean, this is pretty obvious. If we want to be super rigorous, we should do it by induction, but I kind of don't feel like it, so we'll just do the sloppy way. The sloppy way is just to say, look, n minus 1 is less than n, n minus 2 is less than n, and then, you know, just n minus 3 is less than n. Just keep on going until we get to n minus k minus 1. That's less than n also. And so,
Multiply them all up.
yeah, you just multiply them all up. And when you multiply them all up, you get n minus 1 times n minus 2 times n minus 3, all the way times n minus k minus 1. And that is indeed less than n to the, how many of these do I have?
Just one.
K minus 1 of them, right? So this is n to the k minus 1. And then to get the last one, so you just multiply by n. So we get n minus 1, n minus 2, n minus 3, minus k minus 1. Is less than n to the k. And then that proves this. Okay. Everyone with me?
Yeah.
Alright, so back to over here. So now common sense indicates that all that red stuff is less than 1. So if this is an expression for a sub n, I now claim that a sub n is less than, and what I'm going to do is I'm going to replace each of these with just 1, right?
Right.
Yeah. So this is 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus dot 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 1 over k factorial dot 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 1 over n factorial.
So it's basically the Taylor series.
It's some kind of thing, whatever that is. So so that's like something kind of interesting. Yeah, and everyone's got the logic under control, right?
Yeah.
This is less than this because I replaced this with something that's slightly bigger than it by making all these things that are less than 1, 1. Okay, well, now there's only a handful of series that I know anything really solid about, and one of those is like the geometric. We did something kind of like this already. Right, so what I'm going to do is I'm going to write this as 1 plus, this just is a half, and what I want to do is I want to just make this a fourth. No.
That's not a fourth.
I want to make it, yeah, this is, but it's less than a fourth. So this is in turn less than.
Oh yeah.
I want to replace it with a fourth. So
yeah.
so really the claim I'm making, second
Powers
claim,
of 2 are less than the
second claim, camera over here,
Greater than.
zoom in if necessary. K factorial is always greater than or equal to 2 to the k minus 1. For k greater than or equal to 2. And of course, that's kind of just like obviously true again. If you want to prove it, there's tons of ways. The sloppy way would just be to say like, look, 2 is greater than or equal to 2, and then 3 is bigger than 2, and 4 is bigger than 2, and you just go all the way up to, you just go all the way up to k is bigger than 2. So when you multiply all these inequalities together, you just get that k factorial is bigger than 2 to the, how many terms do I have here? Well, I started with 2 and ended with k, so that's like k minus 1 terms, yeah? Okay, so proved. All right, and since that's true, then 1 over k, I guess greater than or equal to, technically. So 1 over k factorial then would be less than or equal to 1 over 2 to the k minus 1. What's up? Yeah, back over here. So now what I'm going to do is I'm going to replace each of these with, I'm going to replace this 3 factorial with 1 over 2 squared. And this is 1 over 2 to the k minus 1. And the final one is going to be 1 over 2 to the n minus 1. Yeah. And what I did is I took term by term, and replaced something with something which is guaranteed to be bigger than or equal to it, right? So this next line must be greater than or equal to the previous line, right?
Yes.
Okay, so I had a sub n. A sub n, I showed that a sub n is less than this, which is in turn greater than or equal to this. So therefore, and what is this crap? Well, this is just a geometric series, right?
Yeah.
This is just 1 plus, I don't even know if I need this step, this is just 1 plus a half squared, plus half to the k minus 1, all the way up to a half to the n minus 1. And which is then equal to 1 plus, now we just do it, right? This is 1 minus 1/2 to the n over 1 minus half. That just is that geometric series. So that's 1 plus